Let's now talk about the blending problem sensitivity analysis on the constraints. In the previous video, I just talked about the variables. So yeah, let's have a look here quickly at two things to start with. The final values and the constraints. What these actually are, if we look back at the problem, it's how much of each resource we used versus how much was available. Notice we satisfied that we needed exactly 8,000 pounds of feed, and then we actually just went to the minimum of corn needed, just to the minimum of grain needed. We needed at least 12,000 pounds of grain, 1,200 pounds of grain, at least 1,600 pounds of corn. We used just those minimums, and then notice that our minerals, we went quite a bit over. Again, our goal is to minimize the cost, so apparently I guess it's not that expensive to have a lot of minerals in the mix. So let's have a look here and see what that looks like when we're looking at our sensitivity report. So you'll notice these three, the final values, equal to the constraints. So a little note here, when final values equal constraints, or constraint right-hand sides, then that, or those constraints, are binding, we say. We use up all of them. Forgive me, let's just fix the font here too. Okay, so these guys and these guys, let's just go highlight them as well here. Make that blue. Highlight this comment. Good. Okay, so when these guys match these, that means we've used up all of that constraint or gone right to the limit, whatever that limit is. Now, actually, let's change the coloring here of this one because we have something different for this bottom row here. So for this bottom row, what do you notice about the final value and the constraint? They are not equal. So when the final value does not equal, doesn't equal to the constraint right-hand side, then that constraint is not binding. So we don't have a problem satisfying the mineral constraint. In fact, we could go 550 above in this case, no problem. Let's also look at these allowable increases and decreases. So what this tells us for this constraint here, let's put this in green here, that's 550. Let's see what that tells us. Okay, so that 550 tells us that we can go up to 550 over this limit and still have the same optimal solution as before. So the allowable increase of 550 means we can require up to 1750 as the minimum mineral content without changing the optimal solution. So that's how much we can make that right-hand side go up to. We can make it increase by 550, which is actually what just happened here. That would put us up at the 1750, which we're at. And we still get the same optimal solution as before. Now, on the lower end, let's look at this decrease right here. Let's color code that guy also. This decrease is a little bit funny. Let's make that pink. So that allowable decrease is a little bit different. The allowable, let's see, decrease here. Just going to edit these words. Okay, the allowable decrease looks a little bit funny here. So it's the, we've talked about this before, 1E plus 30. And what that means is that we can decrease the mineral, or let's say minimum mineral requirement as much as we like, and we will still have the same optimal solution. So we could drop that required mineral content down to 0 even, and we'd still have the same optimal solution. These allowable increases and decreases are only useful when we have a non-binding constraint. And the only constraint that's non-binding is the minerals used. All of the other ones were what we call binding. Our final value is exactly equal to our right-hand side. That's what we talked about at the start here. Whereas this one is non-binding, so this allowable increase and decrease we can use to figure out where our real limits are for our constraint, kind of where they are without changing our optimal solution. Now let's also talk about these shadow prices just briefly. Okay, so let's look at this first shadow price right here. Let's color code it in purple again. So this shadow price right here, what it actually tells us is the following. It tells us how much our constraint, how much our objective function is going to increase for a 1 unit increase in this right-hand side of the constraint. So in this case, if we require 8,001 pounds, of feed. So if we increase this right-hand side by 1 unit, so going from 8,000 to 8,001 pounds of feed, if we now require 8,001 pounds of feed to be made, then the cost, which is what we're looking to minimize, that cost will increase by the shadow price. So in this case by basically 1 penny. So for every extra pound we require of feed, we have to pay 1 penny more. Not too bad, actually. Let's look at this shadow price as well. Okay, and so if we require, in this case, we're talking about the corn used for this one. So if we require, in this case, 1,601, so we're going to increase this by 1, 1,601 pounds of corn in the feed. It will increase the cost by 50 cents. Or we could say the cost will increase by 50 cents. So the cost is going to go up by 50 cents if we require 1,601 pounds of corn in the feed. And same with the grains, same idea. If we increase the pounds of grain up to 1,201 pounds, we're going to require, or we're going to have our cost go up by 87 cents. Okay, so here we go. I just wrote this out. Just hit pause to save time. And so yeah, if we require 1,201 pounds of grain in the feed instead of 1,200, so we increase it by 1 unit, our cost is going to go up by roughly 88 cents. The final one here, the minerals used. If we require more minerals used, well, that's fine. Notice we're at 1,750. So if we increase the required mineral content to 1,201, well, who cares? The cost increases by $0. Notice we're already up at 1,750, so who cares if we require it to be 1,201? That's not going to make any difference. We're already way over that. So for the non-binding constraint, it makes no difference. Notice the shadow price is 0 because there's no extra cost for having a requirement of more minerals. We're already way above the minimum requirement. Okay, and that concludes our sensitivity analysis for the blending problem. Thanks for watching.